Hi students. In this lecture, I am going to discuss problems from HC Verma. Let us see first one. Figure shows a spring fixed at the bottom end of an incline of inclination 37 degree. A small block of mass 2 kg starts slipping down the incline from a point 4.8 meter away from the spring. The block compresses the spring by 20 centimeter, stops momentarily, and then rebounds through a distance of 1 meter up the incline. You can see diagram here. Find the friction coefficient between the plane and the block. And second one, the spring constant of the spring. And G value 10 meter per second square. Let us see how to start. At first, make the given diagram. So diagram is given inclination 37 and keeping one spring at the bottom of incline. A spring is fixed at the bottom end of the incline. And let's see here. This is now block. So first, see mass given how much? 2 kg. You can see distance from here to up to here. That is given 4.8 meter. Okay. And spring compresses by 20 centimeter. Spring compresses by 20 centimeter. So we have to calculate now what is the coefficient of friction. It is actually coefficient of kinetic friction. Next, we have to find coefficient. Then we have to find spring constant. Okay. And one more condition given that after compressing the spring, it moves up 1 meter. It moves up 1 meter. Let us see. See how we are starting the problem. So first thing we are focusing that block starts from rest. It moves down, compresses by 20 centimeter, and again moves up 1 meter and comes to rest. Okay, you can see once here. Suppose this is position A. When spring compressed by 20 centimeter, take it as P. Finally comes to rest. From there to it covers up a distance 1 meter. Okay, from A to B, from B to C. A to B, it is 4.8 plus 0. Okay, that means AB value 5 meter, BC value 1 meter, AC value 4 meter. Okay, I hope you got clarity. AB, BC, and AC. Okay, now see what I'm doing here. First, I'm taking A to B and B to C. That means in the entire journey, starting from rest and finally comes to rest. That means delta K equal to 0. Since delta K is known, I am writing here work energy theorem. net work is equal to delta K. Okay. And you can see when this is moving down the incline or moving up the incline, because of, you can see because of normal reaction, no work is done. Okay. Work is done only by gravitational force. Gravitational force. Next, work done by frictional force, by spring force, totally equal to zero. And if you observe carefully, compressing the spring by 20 centimeter and again it moves back, means again spring comes to natural state. So while compressing by spring force on the block, work done is negative. And when block moves up by spring force on the block, work done is positive. And these two will get cancelled. That means by spring force, work done is zero. So I hope you got clarity. While compressing by spring force, negative work is done on the block. While moving back by spring force on the block, positive work is done. And both are same. Means values are same. One is negative, other one is positive. So net value C. Okay. And remaining is only by gravitational force and by spring force. Okay. Let us see now calculation part by gravity. Since gravitational force is a conservative force, we have to focus what is initial position and what is the final position. Initial position is A and the final position is C. So displacement how much? A to C, it is a 4. Displacement is a down. And you can see weight component mg sine theta, that is also downwards. That means because of gravity, positive work is done. Okay. And because of friction, negative work is done. So I'm writing here mg mg sine 37 into displacement is 4. This work is positive. Because of frictional force, mu mg cos 37, frictional force, kinetic friction, displacement. We should not write here displacement because while moving down from A to B, negative work is done. That is minus mu mg cos 37 into 5. While moving from B to C, again negative work is done. So I'm writing minus mu mg cos 37 into 1 totally equal to 0. So focus very carefully. When it comes to gravity, I have taken directly displacement A to C 4. But while taking by friction, we should not take directly displacement because A to B while moving down by friction, negative work is done. How much? Mu mg cos 37 into 5. While going up, again negative work is done. How much? Minus mu mg cos 37 into 1. Okay. This total value is 0. Throughout mg gets cancelled. Remain just calculation part. mg, mg cancelled. Sin 37 3 by 5 into 4, that is equal to. Now take sum of these two. Here what is left? Mu is there. Here also mu is there. Cos 37. So mu into cos 37, 4 by 5. This is a 5 and this is 1. Total is 6. Okay. 5. 5 gets cancelled. 4. 4 cancelled. Mu equal to 3 by 6. 1 by 2. Okay. That is our answer. Now we want to calculate spring constant. Now to find the spring constant, see what we can do. I am focusing only from A to B. Focusing only A to B. In that case, we can involve spring force. Okay. So again writing net work equal to delta K. Delta K 0 because starting from rest coming to B comes to rest temporarily. Okay. So by gravity, work done. By friction, work done. By spring force, work done. Net equal to 0. Okay. Now see what I can write here. By spring force, it is negative work is done. Okay. So by gravity is how much? I'm taking directly values here. mg sin 37. mg sin 37. And first see here. mg sin 37. Displacement equal to 5 because A to B it is a 5. Okay. By friction minus mu mg cos 37 into 5. Okay. By spring force minus half k x square x value 0.2 whole square because compression is given 20 centimeter. So converting into meter 0.2. Now substitute values in that. mg means 20. Sin 37 3 by 5 into 5 that is equal to mu value half mg 20 cos 37 4 by 5 into 5 plus this is how much 4 10 power minus 2. Okay, so 2 here, so 2 10 power minus 2 into k. Okay, now remaining the calculation part. 5 cancel, 5 cancel, 2 here 2 times 20 into 3 16. This is a 40. 60 minus 40 20. 20 equal to 2 10 power minus 2 into k. 2 10 times 10 power minus 2. That means k value 1000 Newton per meter. Okay. So in the first part, we have taken complete path A to B, B to C. So advantage was no involvement of spring. Second case, we require spring constant. That's why we have taken only downward motion. In both cases, we have taken net work equal to 0. What can I achieve theorem? Okay. So how to identify means? Because we are knowing delta K equal to 0. Okay. Let us see next one. Let's see the question. One end of a spring of natural length h and a spring constant k is fixed at the ground. You can see here. And the other is fitted with a smooth ring of mass m, which is allowed to slide on a horizontal rod fixed at a height h as shown. Initially, the spring makes an angle of 37 with the vertical when the system is released from rest. Find the speed of the ring when the spring becomes vertical. Okay, let us see how to start. So first make the given diagram. So with vertical, initially spring was making an angle. It was making an angle 37. It was making an angle 37. Now, when spring becomes vertical, we have to calculate speed of the ring. Okay. See here what we are doing. Initially, ring was stationary, so no kinetic energy. When it comes to here, we have to find the speed. Means we should know what is the kinetic energy. That means so we can use now work energy theorem. So I'm writing here work energy theorem. So W net is equal to delta K. Okay. Now see here. For the ring, there is no change in the height from ground. That means no change in its gravitational potential energy. Or we can say by gravity, no work is done. Because gravitational force is vertically down, but displacement is horizontal. Okay. Next, normal reaction by the rod on the ring. It is along vertical. Again, by normal reaction by rod on the ring. No work is done because normal reaction is vertical. The ring is moving horizontally. So again, between force and displacement, between these two vectors, angle is 90. The remaining is only spring force. So work done by spring force equal to delta K. Okay. So by spring force work done, see how much? By spring force work done. Or we can say like this. Instead of calculating work done, I'm using directly conservation of mechanical energy. Okay. Because since rod is smooth, there is no energy loss. Initially, spring was having elongation. So spring was having potential energy. When spring becomes vertical, no spring potential energy. This loss in spring potential energy converts into kinetic energy for the ring. Okay. So I'm writing here half K x square elongation initially. How much? This is a h. This value will be that is h by cos 37, right? Hypotenuse. That is 5h by 4. So present length 5h by 4. Initial length h. So elongation equal to 5h by 4 minus h. That is equal to half mv square. So whenever it is possible, the best one is writing energy equation, means law of conservation of mechanical energy, because energy is a scalar quantity. Okay. So first priority is given to conservation of mechanical energy. Right. Now see what we can do. 2, 2 cancel. This is h by 4. H square by 16. So k h square by 16 equal to mv square. From that we equal to, it is k by m under root into h by 4. So it is very simple and direct one. Okay. Let us take the next one. See the question given. A simple pendulum of length L having a bob of mass m is deflected from its rest position by an angle theta and released as shown. The string hits a peg which is fixed at a distance x below the point of suspension, and bob starts going in a circle centered at the peg. Okay. Assuming that initially the bob has a height less than the peg, show that the maximum height reached by the bob equals its initial height. So this we can say directly by using conservation of mechanical energy. You can see diagram here. If you have in this way, see, if it makes angle theta, again this side you can observe it will reach the same height, because when there is no loss in the energy, There is no change in the height when it comes to rest. Okay. So first one we can see directly by using conservation of mechanical energy. Now focus remaining two parts. If the pendulum released with theta equal to 90 and x equal to L by 2, find the maximum height reached by the bob above its lowest position before the string becomes slack. Before the string becomes slack. Okay. So this is based on vertical circular motion. Okay. And next one, find minimum value of x by n for which the bob goes in a complete circle about the peg when pendulum is released from theta equal to 90. Now see carefully. So first make a diagram. See the diagram given. String is like this. Condition given that theta equal to 90. Okay. When theta 90 means a string initially horizontal. Okay. Horizontal. Given that x equal to L by 2. Given x equal to L by 2, theta equal to 90. So x equal to L by 2 means string is horizontal. I'm making diagram once again here. You can see this is now the initial position of the string. When string becomes vertical, its velocity becomes root 2zh, right? Root 2zh, h equal to L, right? This is L. Now there is a peg. There is a peg. Peg means just like we can say one hook, okay? There is now one hook here. Then what happens is once string becomes vertical, this part of the string cannot oscillate. Only remaining part will move. Okay. So condition given that this will oscillate about this peg. Means taking the peg as center. That means this follows now circular path of radius L by 2. Okay. That means this velocity in terms of radius. This is 2g into L by 2 into L. Okay. This is now root 4gr in terms of radius. And we have learned that if velocity is root 5gr at the bottom, it is able to complete a vertical circle, right? That means now in this case, vertical circle is not possible. Okay. Then see what we can say. If it is able to complete one circle, we can say suppose it makes angle theta with upper vertical. If you remember now, see height from the bottom. Height from bottom means suppose this is center C, this is taken as C, and this is B. Height equal to AC, that is R, plus this value, this will be R cos theta. Okay. R cos theta, the value of cos theta. If you remember, while discussing vertical circular motion, in that we have learned cos theta equal to u square minus 2gr upon 3gr. This is what I have discussed while discussing vertical circular motion. Okay. When string slacks at that time, angle made by string with upper vertical. Now I am using that result here in the place of u 4gr. 4gr minus 2gr remaining 2gr upon 3gr. Gr cancel. It is now 2 by 3. That means h equal to, here r value how much? L by 2. L by 2 into 1 plus cos theta value 2 by 3. Then h value how much? 3 plus 2 5. 5 by 3 means 5L by 6. That is a height reached above point A, means from bottom. Now coming to the second one, it is also very simple one. Using same logic, only change here given x equal to L by 2. Now in this case, x we have to find out. So here what I can do here, in the place of velocity root 2gl, no change in that root 2gl for third part. Coming to here, if this velocity equal root 5gr, root 5g, given now this peg is at a distance x. So remaining how much? L minus 6. So r equal to L minus 6. Okay. So if that velocity equal to root 5gr, then it is able to complete vertical circle. Okay. Now square on both sides. G gets cancelled. 5L, this is 2L. 5L minus 2L, that is 3L. 3L is equal to 5x. Okay. From that, x by L is equal to x by L equal to 3 by 5. That means 0.6. For this ratio, it is able to complete vertical circular motion. Okay. So I hope you got the clarity. So option C, right? C, find the minimum value of x by L for which Bob goes in a complete circle. Right?